All right, so I've had a couple of people ask me how to do this question, 4.10 from the transport PDF book. So it's to do with a train that's traveling at 120 kilometers per hour and weighing 400 tons. So firstly, calculating the kinetic energy and then working out, if you know the power of the engines, how quickly it's going to get to its top speed. So the questions are related. Obviously, you have to do part A to be able to do part B. Um, so I'm just going to step through how to do that to help you guys out. So firstly, asking for the kinetic energy. So if you guys know the formula for kinetic energy, um, I can't remember the exact terminology because I don't have it in front of me, but uh, pen. So energy kinetic, uh, still learning how to use this pen, is equal to half times mass times velocity squared. Okay, so then it's just a matter of making sure that our values that we've been given are correct to be able to put into that. So we've got mass is equal to 400 tons, which isn't an SI unit. So we need to convert that. So a ton is 1,000 kilograms. 400 tons is 400,000 kilograms. And the speed or the velocity is equal to 120 kilometers per hour. Should have a little p, sorry. Again, not an SI unit, so it needs to be meters per second, so we can times that by 1,000 to get it to meters. So 120,000 meters per hour, and then divide it by 60, and then by 60 again to get it to meters per second. So 120,000 divided by 60 divided by 60 is equal to 33.33 meters per second. Now we can plug those values into our formula and get the kinetic energy. So EK is equal to 1 over 2 times by 400,000 times by 33.33 squared, which is equal to, you can't see my calculator, but just going to trust me, or you can put in yourself, half times by 400,000 times by 33.33 squared is equal to 222177780 joules. That's the unit for energy. Because it's such a huge number, we can make it kilojoules or megajoules. So just take off blocks of 3. So that would be kilojoules. That would be megajoules. So I'm going to do it to megajoules, 222.2 megajoules. Put that in, 222.2 megajoules. Capital M for mega, that's a little m for milli. Alright, so now I've got that, I'm just going to get rid of this, I've got a bit of room. And move on to part B, which is the interesting part anyway. So to do part B, you need to know that power is a measure of a change in energy divided by time. So as the train speeds up, its kinetic energy increases. So from 0 when it's stationary to this value here, 222.2 megajoules when it's at its top speed. So the more powerful the engine, the faster it's able to give it that kinetic energy. So you kind of can understand that as, get a blue pen, power equals change in energy divided by time. Change in energy should be in joules or megajoules or kilojoules, and time should be in seconds. Power, whatever prefix, I think the word is, you use for your energy, you should also use for power. So it can be watts equal to joules divided by seconds, or kilowatts equal kilojoules per second, or megawatts equal megajoules per second. So for cars, we're used to kilojoules. Might have a 200 kilojoule, kilowatt engine, or something about that, or maybe a bit less. Okay, so now it's just a matter of putting it into the equation. So if power is equal to change in energy over time, so our change in energy equals 222.2 megajoules, because it starts with 0 and it speeds up to its stop speed. Power is equal to, so it's 150 kilowatts per engine, and there's 16 engines or motors. So 16 times by 150 kilowatts, which again, you're just going to have to trust my calculator. 16 times by 150 equals 2,400 kilowatts, which, in order to have my joules and my watts in the same, I'm going to convert that to megawatts, 2.4 megawatts. And then we're all good to plug these values in. Okay, so if power is equal to change in energy over time, so we've got 2.4 is equal to 222.2, and there's going to be a slight rounding error here because I've rounded my kinetic energy. You could put that in unrounded if you want, but it'll be okay either way. 222.2 divided by time, which we can do as t. So now it's just algebra. So time is equal to 222.2 over 2.4, which is equal to 222.2 divided by 2.4, 92.58 seconds, or that would be 1 minute and 33 seconds rounded up. So 1 minute, 33 seconds. Obviously, that's not an accurate value in real life, because as the train speeds up, it's actually going to be encountering a lot of air resistance, so its acceleration will decrease as it gets faster, up until the point where it reaches its maximum velocity, which should probably be where the amount of wind resistance it's facing is equal to the amount of energy that its motors are able to put in, unless its maximum velocity is determined by something else like the track maximum speed or efficiency or something like that. So as the wind resistance increases, the kind of net power or gross power that the train is experiencing, causing the acceleration, will actually be decreasing. But this will do for us. I hope that helps, and I hope you guys are enjoying your holidays. See you.